All right, back for part 2 of the ear. So we finished the structures and functions. If you have questions, please let me know. Otherwise, we are on to the 2 hearing theories that we have to look at. So this is not a theory. This is just about our ability to hear. So when we look at how we locate sound, meaning if I were to close my eyes, how do I know which direction sound's coming from? Or even if I don't close my eyes, when I hear a sound, I know if I need to look this way or that way, or like which direction. I generally know which way the sound is coming from. And so the 2 cues I use are which ear heard it first and which ear heard it louder. Right? So if it's coming from this direction, both ears will eventually capture the sound, but this one hears it first, and it's going to hear it a heck of a lot louder because it's getting it right here versus this ear has all this other stuff to wait for, right? So those are the 2 cues we use when it comes to how to locate sound. Now, the 2 theories about how we pick up different pitches, that's what hearing theories are. How do we hear a high note versus a low note? How do we distinguish? And so the first one is place theory. So the guy who proposed this was Hermann Helmholtz. If you remember from the eye, the young Helmholtz theory was the trichromatic color for how we have vision, how we see colors. He also came up with the hearing theory. And so his thing is called place theory. And it says that specific frequencies or specific pitches are going to pick up on different parts of the basilar membrane. So I think this drawing up top does a really good job. If we look at our inside of our cochlea here, the swirly one, this long one, it's just like if the cochlea, if instead of being rolled up, we like stretched it out. And so if maybe I hear really high pitch notes, frequencies, really high, it's going to be down on this end. And then if I hear like really low notes, it's going to be way up here. Okay, it's the place. It's saying that different places on the basilar membrane inside the cochlea, so different places where hair cells are located, different places have different pitches, right? And that makes a lot of sense. And then tones are picked up by the brain based on what part of the cochlea was stimulated, where on it. So place is the where. Where on the cochlea, where on the specifically the basilar membrane, because that's where the hair cells are. Which hair cells are being stimulated. Frequency theory, I don't have a pretty picture for because I couldn't find one. It's not about where on the cochlea is being stimulated or where on the basilar membrane. It is about how quickly are the hair cells being stimulated. So think of the basilar membrane like a drum head again. And if I hit it really slow, the hair cells are just going to be like, right, really low notes. Maybe they're really slow. Versus if it's a really high-pitched noise, the wavelengths are faster. And so maybe the hair cells wiggle more. And so the frequency, how fast or how much are the hair cells moving, depends on what sound you hear. The hair cells move really chill and slow, it's a low sound. If it moves really, really fast, maybe it's a high sound. So once again, we don't have an answer of which one's the correct one. We have no clue. They both have their merits. All right, we also talk about hearing loss in this unit. And so we can talk about sensory neural hearing loss, which is nerve deafness, but the correct term is sensory neural hearing loss. Nerve deafness is just like an easier term to understand what it means. And this is when either the hair cells or the cochlea are damaged, so like your actual hearing organ isn't working, or the auditory nerve is damaged, so you no longer are getting those signals sent to your brain. With this thing would have to be circumnavigated or quote fixed with a cochlear implant where they go in and it's kind of like they give you a fake cochlea in some regard, where they implant it in your head, and it looks like you wear a hearing device, so it's like a battery pack, but it's actually implanted on your head, and then there's like a pacemaker thing they put under your collarbone. And so it kind of like short circuits things. So if your cochlea or whatever is not connecting with your brain or your auditory nerve's not working, maybe you can use this. There is a kind of an opposition in the deaf community when it comes to children who are born deaf. They don't think those kids should get a cochlear implant right away, it seems, because people that are deaf don't see it as a disability. It's just a different ability. and they, you know, they have their own language. They have sign language that they can use. So a lot of proponents in the deaf community will say that kids need to learn sign language and learn grammar and all that stuff first before going and getting a cochlear implant put in. But, you know, people do it when their kids are little. Some people never have one. It doesn't work for everybody. It just really depends. And when somebody gets a cochlear implant, especially if they're older, they have to learn language. So if somebody was born deaf or deaf before they learned how to speak, maybe that, like, I know this is a cup, right? It's a cup. I can close my eyes, and if you say cup, I know exactly what you're talking about. If somebody is deaf and they have been their whole life, when they hear the word cup, they've never heard that sound before. They might be able to read lips, but if you had them close their eyes and say, tell me what a cup is, they won't understand that. So they basically, it's kind of like relearning language. Their brains are still able to, because they've been exposed to the rules of grammar and spelling and all of this stuff, and the ability to read. They have that down, and so their brains are still wired, being able to understand and learn language, even if they get their cochlear implant at the age of 20. It's still like they have to learn, though. And then we have conduction hearing loss. This is when the mechanical systems are broken prior to getting to the cochlea. So this could be like a damaged tympanic membrane, or the ossicles aren't functioning enough. It's kind of, I always think of it like you just need a stronger impulse to get it down there, because whatever wavelengths are happening, it's not helping. It's not deafness. It's hearing loss. And so this would be somebody like is hard of hearing, and you have to yell in their ear to get them to understand. They need the stronger amplitudes to get in there. And so hearing aids are often used because it's just like almost like a loudspeaker that they plant in your ear to increase your ability to hear things, because something is not working correctly. And that's why a lot of older people, as they get up there in the years, they may need a hearing aid. It could be they damage their hearing over time. It could be that, just like we talked about, your lens gets less flexible when you age. So does your tympanic membrane. That barrier gets a little less wiggly. It doesn't react to stuff as much. So you get a hearing aid, so then it like really gets in there and gets the message across. So all of this stuff is just a hearing loss rather than a deafness. And often people need hearing aids to help out with it. So if we look at the word audition, if you see this, remember it means hearing. And we just mentioned this. Older people tend to hear at lower frequencies well, but suffer from hearing loss to higher frequencies. As we age, our ability to hear it goes downhill. Usually like 60, 70 is like the age where we see things go way downhill with our hearing. I think hearing even has an earlier age range on it. We talk about it when we talk about development. But yeah, hearing is something that we want to protect as much as possible. Yes, there are mechanisms we can use to help us out, but it'd be better just to preserve it if we can. All right, that is it for the ear, and hopefully we're good to go. All right, let me know if you have any questions, guys. Thanks.